Good afternoon. I hope everything is going okay by you. It's a beautiful day outside. Unfortunately, it's still a day of social distancing outside. I'm ready to get started continuing along in the angle modulation chapter. I can take questions, last minute comments on the project. Three have been turned in already, so I'm expecting two more. I'm expecting if Colton and Will are working together, I'm expecting your project, and then I'm expecting Chris's project. So let me know what's happening there. I'm not going to talk about the project unless somebody brings it up at this moment. And what most everybody's been turning in has been just fine. Sending it on Slack is most excellent, because that way I can just move it quickly. I'm finding out that shuffling papers and storing them and being able to pull them back up, getting them over to my tablet so I can grade them, is taking a little bit of getting into the routine, but I think I've got it down now so that I can do that and then manage to put things in a pile called graded. I don't have anything to give back to this class right now, but I was working on another class yesterday. It's more time consuming than I thought it would be, just to take your files and get them stored in a safe location and then have them ready to go. At any rate, the big news on the website that I pushed a notice onto Slack earlier was that I decided I would just dump everything out for the rest of the semester in terms of homework. This way, I feel like I can get to work on grading better. I still have to answer questions, of course, but I won't be pondering this anymore. I just pushed it out there. So 9, 10, 11, and 12 are up there. I've got hints for everything except 12. 12 is Appendix A, which is a rather easy and straightforward chapter to go through. And then there's also project number 2, which will be actually a much easier project to work through too. There's very little coding in project 2. There's mostly just running pre-built code and doing experiments with it, and then assessing some of the things that you measure. So you don't write hardly any code at all in Project 2. And it actually goes by pretty quickly, and you're investigating digital communications the whole time, which is fairly exciting and interesting. Something else that is also on my mind is thinking about the calendar and thinking about Exam 2. We do have an Exam 2 in the class, and I think I pushed it up into assignment 10. I guess I can just quickly check that. If I go down here and look at assignment 10, no, it's not in assignment 10. Well, which one is it in? Maybe it's in 9. I'm kind of not thinking exactly because I did this a few hours ago. Yeah, it's in 9. So I'm proposing days for Exam 2. So I see here the 23rd, 28th, and 30th. And I'm guessing no one's going to want to do it on the 23rd, but I decided that would be the earliest that I would be willing to do it. And then 28th and 30th are the next two options, the way I see it. Final exam week is down here, the second full week of May. And I don't want to be doing anything on this week with exams. So the 28th or the 30th are probably going to be our prime candidates. We don't have to answer that question right now. But I will talk a little bit about my thoughts on how I'm going to do the exam. I'm not going to expect you to have proctors, but what I am going to do is give you a very short time window. I'm going to put you under an honor code. I'm definitely going to want you to be very honorable and not be talking to each other during the exam. I could put cameras on you and ask you to do that, but something tells me that that may be an awkward thing to get to work well. But it will be time limited, so it will be given to you, and we'll have to discuss, and you'll have to give me feedback how it is that you're going to be able to write on the exam, because it'll come to you electronically, and then you'll have to print it, or you'll at least have to answer the questions by writing on some blank paper. So that's something to start thinking about and giving me some ideas. I'm hoping that most of you will have a printer, so that if I print the exam out, say 2:45, or post it on Slack 2:45, you'll be able to print it, and then you'll be able to get started right away. And then, of course, when you're done, I will have some sort of a system where I'll say done, and then it'll be like at 4:30, and then you'll have like 10 minutes or something like that to get it scanned on your cell phone or on a desktop scanner if you happen to have one of those machines at home, and get it sent back to me. So that's kind of the plan. Good topic for discussion on Slack, not while I'm lecturing, but if you want to give me some ideas how you see it working or how you would like to see it work, I'll take your inputs and thoughts on it, because I know some of the other classes have been giving exams since the week before spring break, is my understanding from what other faculty reported on. So want to head in that direction, and then the final exam will run the same way. It will be a 2-hour exam, and it will be during finals week, and it's comprehensive the way I've done it in the past. So without further discussion, I'm going to switch over to Jupyter Lab just so I can be ready to look at some of the calculations. And I'm going to go along a little ways in here, and then I'm going to switch to talking about the homework. I have my solution sitting here on my other computer that we can look at, the 3 problems, and I'm willing to go through some tips on working the homework. Some of the tips are already in the Jupyter Notebook, but one of the problems, number 13, is not. So we left off talking about angle modulated signals. We had been through sinusoidal angle modulation. Then we had talked about the general expression for bandwidth. So sinusoidal modulation was the Bessel functions that we had here, and we have these plots, spectral plots that I made, and are also available in the Jupyter Notebook. And then we came along and talked about the bandwidth of an angle modulated signal, and came up with these equations right here. Carson's rule is what we came up with. So this is probably our principal expression for getting the bandwidth of an angle modulated signal. If the signal happens to be a single sinusoidal tone, then bandwidth is this equation right here, but we can see that beta, which is the rule for sinusoidal modulation, beta being, let's see, for FM modulation with a sinusoid, beta is FD, the modulation index, divided by the modulating frequency times the amplitude. And I'm going to be playing with that some in the simulations stuff that I'll show you today. But what I was getting at over here is beta and D serve the same role in the bandwidth expression. D is the generic for a message of some bandwidth W. So we calculate D using D equals deviation constant of the modulator, say so many hertz per volt, divided by the bandwidth, then times the maximum value of the message. And then last time we also talked about this alternate form, that the bandwidth can also be calculated as twice the quantity W plus delta F. This is a very useful alternative because it actually gives you insight into what the frequency deviation is doing. So, and I talked about this before, but it lets you see that if we were looking at ordinary single sideband, or double sideband I mean, we'd start off with something like that, and we'd go minus W to plus W, so we get the bandwidth as being 2W, where the carrier is sitting right in here. And that's, of course, that term right there. And then as we bring up the deviation from a narrowband scenario where it's imperceptible, I mean, it's a very small amount of deviation, then the bandwidth starts to expand beyond the 2W. So we get this 2 delta F is the expansion factor due to the angle modulation, making the bandwidth grow well beyond what we would have seen for double sideband modulation back in chapter 3. I think that's really helpful. It helps you kind of lock that in your brain. So here's an example I put up for FM broadcasting. And in FM broadcasting, carrier frequencies are on odd multiples of 100 megahertz. So this is 101.1. I don't know what station that is in Colorado Springs. Some of you might know. Does anybody know? 101.1. If you don't know, that's fine. But the peak deviation, or the deviation constant in analog broadcasting of FM, is 75 kilohertz per volt. So the beta value, the aggregate effective deviation value, D, for broadcasting is 75. So if I just put in a single tone and want to bring that up to beta of 75, I plug it into the equations like so. I have FD over FM times A, and if I go ahead and plot that spectrum, this is what the spectrum looks like for a 1 kilohertz tone. Here I'm putting in FM of 1000. You can see it's nice and fat. I mean, it's running from about 76 kilohertz below the carrier to 76 kilohertz above. And that fits within the allocation band for broadcast FM, because broadcast FM has the station spaced every 200 kilohertz. So we have a 101.1, and then we'd have another station at 101.3, and then below that we'd have a station at 99.9. So I'm not going to be able to draw that very well if I do it like I just started to do there. So that's the way the FCC allocates channels in the FM broadcast band. And we'll get into FM broadcasting more later when we end up talking about frequency division multiplexing, because we'll talk about how FM stereo works and how other subsidiary broadcast services actually exist inside of the FM signal. And that's kind of an exciting thing. And when you work Lab 6, for those of you in the COM lab, whether or not you buy the dongle that I recommended that you obtain for $20, you'll be using captures that Daniel will provide from live stations. And when you unpack that signal, you'll be able to get inside of it and see spectrally, and then you'll be able to process the signal and recover the stereo information by working with the subcarrier. And I'm not going to go off and discuss that yet, but we'll get to that eventually towards the end of this chapter. So before we go further, though, we're going to do a calculation which is kind of like a calculation in one of the homework problems, and that's this question that's posed right here. So let me clear this stuff off that I scribbled. Suppose our broadcast signal is sent through a bandpass filter that's got a bandwidth of 11 kilohertz, total bandwidth of 11 kilohertz either side of the 101.1 megahertz carrier. So we could use an ideal bandpass filter, which would be a rectangle at plus FC and minus FC. We're making the total bandwidth 1100. So just to zoom in on that filter, So if this total bandwidth is 11 kilohertz, then we're talking about 5.5 kilohertz either side. Somebody's got their microphone turned way up, and I'm hearing all your household noise right now. Does anybody want to take care of that? So I'm going to do, there we go, it's gone. Well, it's back again. So 5.5 kilohertz either side. So for the case of the 1 kilohertz tone modulating the carrier, FM-wise, the sidebands are going to occur at multiples of 1 kilohertz. So we're going to have a tone on the carrier, 1 kilohertz above, 2, 3, 4, and then 5. And then beyond that, the filter is cutting off, so the sideband that's at 6 kilohertz above and 6 kilohertz below is not going to pass through. So if we wanted to find out how much carrier power passes through that bandpass filter, we can go back to our Fourier series expansion for sinusoidal FM, and we know we have the total power in the carrier is AC squared over 2. Remember, that's a constant envelope signal, so it's just the amplitude squared over 2. But then if we want to find out what fraction of that passes through that bandpass filter, we get the power in the carrier, which would be J0 squared with beta of 75. And then we would add up the power in all the sidebands, and since they're symmetrical power-wise, we have to multiply by 2 and then just sum from 1 to 5. So that gives us 241.93 watts out of the total power of 5,000 watts. And that calculation I carried out over here in the notebook using the J/N Bessel function. And I rewrote the equation here, and I just simply plugged it in. I created an array that contains the Bessel function values running from 0 to 100, but then I stepped it down to just take the value at DC, which is effectively the carrier, which is 0 index, and then I sum from 1 through 6 to get the sidebands above that. And pause for a second here, think Python versus MATLAB. You're probably seeing 6 and saying, wait a minute, I don't want to include 6, I just want to go up to 5. Well, this is the way you do it in Python, because when you do the colon operator, you're going to go from 1 up to 1 less than that index. So it's going to go 1, 2, 3, 4, 5, which is what we want. And it gives us the 241.9323 watts. Does that look okay to everybody? This should say 11 kilohertz, I guess. This was modeled after the example that's in the notes, so I just needed to scale it to kilohertz because the tones were at 1 kilohertz, so the harmonics are at multiples of 1 kilohertz. Okay? So I'm going to jump back over here to the notes now, and the book does talk through this a little bit. It's something that just shows you how crazy it can get if you want to perfectly model the spectrum of an angle modulated signal. So suppose we want to consider 2 tones. So here we have 2 tones for our message, and that's a test signal, but actually 2-tone modulation is used in some signaling schemes and telemetry schemes that are part of the Air Force Satellite Control Network, or at least they do tone ranging and other things with multiple tones. It sounds strange, but this is part of the legacy of the way things are done in satellite communications. And also, I worked on a project many years ago for a ranging system or a signaling scheme for missile ranges and flight test ranges. It's was called the flight termination receiver. Does that sound intriguing to anybody? Flight termination receiver? If you don't want to say anything, that's fine. What the project was, though, is down at White Sands Missile Range, if they're testing a missile on the range, and the missile is going to fly off the end of the range, which would not be good, they have the capability to terminate that flight so that the missile for sure safely lands on the range. And that's called the flight termination receiver. And one of the earlier versions of that receiver used multiple tone FM modulation to send the command. The range commander is allowed to terminate anything that appears to be going askew, so objects don't fly off the range and cause damage to property and people. At any rate, this is a two-tone scheme, so if we put two tones up for our phase modulation, two sinusoidal tones, we can look at what the modulation looks like inside the argument of the cosine. So we have phase modulation from tone 1 and phase modulation from tone 2, putting it into a complex sinusoid form. We can go through the same Fourier series expansion we did before, so we're going to have two Bessel function series expansions. And when we substitute that back in, we have this wonderful product of sums. And when we have a product of sums, we have equivalent to an infinite dimensional matrix number of terms, because when you multiply one sum by another sum, you get all of the cross terms included. So you get this double sum, which is, the way I like to think of a double sum like that is if it's over a finite number of indices, you're generating a matrix full of values, and then you're summing up all the contributions from each element in this two-dimensional matrix. So this is what it looks like in terms of the transmitted signal with double tone sinusoidal modulation. So you're going to get all these sums and differences, which is kind of like the intermodulation idea that we looked at back in chapter 3. You're going to have all the harmonics and intermodulation stuff. We have n times omega 1 plus m times omega 2. And if you put that together into a model, this was originally done in Mathematica, but I'm going to show it to you in Python in a moment. This is what it looks like. In this particular case, I set beta equal to 2 for each tone, and then made one tone 10 times the other tone, and then just looked at the spectrum that I get centered on the carrier. So this is shifted so that the center of the plot is actually the carrier frequency, and this is like a one-sided spectrum. So you see clusterings of sidebands because you've got the smallest spacing relates to the lower frequency, and then the bigger cluster spacing relates to the higher frequency, is the way I look at it. Another thing that I did here in the Jupyter Notebook and just thought about is what does angle modulation look like if we just take a narrowband noise spectrum, just a flat noise spectrum, kind of like you were working with in the project, and send it through an FM modulator. So in this particular case, I generated that in Jupyter Notebook as well. So we're going to go look at both of these scenarios right now. So first we'll look at the band-limited noise scenario. So just, this is a curiosity thing and something that should kind of be on your mind a little bit, saying that I know if I put in a single tone into an angle modulator, I get the Bessel function, line spectra. Carson's rule says that if I put in a general message that has such and such bandwidth, say W, I'm going to get a bandwidth on the carrier that's occupied by the modulation that's 2 times the quantity W plus delta F, the peak frequency deviation. So with that thought in mind, let's just see if that applies. I'm going to design a fairly high order IIR digital filter, kind of like you were doing in the project. I'm going to set its cutoff frequency at 1 kilohertz and have its stop band at 1200 hertz, have it be down 70 dB at that point, so I get a fairly good size IIR filter, 16th order. Go ahead and look at its frequency response, and it looks kind of like a brick wall filter because it drops off very rapidly. It's already down 100 dB, and you see the little fine ripple in the top. So now let's just think about how we would simulate angle modulation, and this is something that you'll probably utilize in a homework problem, or maybe we'll be utilizing, well, I know we'll be utilizing later when we're studying phase lock loops, because we'll want to generate an angle modulated carrier. So the top equation, and this is not in the notes, it only occurs here in the notebook, the top equation is the original FM modulator equation, where we integrate the modulation and multiply by the deviation constant FD, and then of course to get things in radians we're multiplying by 2 pi. So now I'm going to convert it to a complex sinusoid form and taking the real part of it, and then I'm going to break the carrier away from the second complex exponential, which contains just the modulation. So I can't draw on this with my pen because this is the Jupyter Notebook, but the second exponential would be called the complex envelope that we've talked about since chapter 3. So it's the complex envelope which is imposed by the modulation M. And if I want to model this in the discrete time domain, I have to take the time axis and discretize it into sample-spaced values. So in this case, I'm using a sampling rate of fs samples per second. So the d alpha here is replaced by 1 over fs, and then the integral is replaced by a sum. So I'm summing all the values as I sample m of alpha at every 1 over fs seconds. And that is a simple discrete time implementation of an angle modulator or phase FM modulator, frequency modulator. Does that look reasonable to everybody? I'm just simply discretizing. So now I can build that in Python, and the main key in building this in Python is the carrier is not a problem. If I just want to represent the complex envelope, and I call this complex baseband or complex envelope, this running sum, which you can see is not a sum that just starts at 0 and stops at n. It's continuously, so it's a cumulative sum. So in MATLAB and Python's NumPy both, we have this function called cumulative sum, and that's exactly what it does. It's a running sum starting with the first value, and then the next output index is the sum of the first two, and then the sum of the first three, and so on. So it's a beautiful operator for doing this exact mission. And then we divide by fs because that is the d alpha in the approximation to the integral. So I put that together. I'm going to generate 100,000 samples of white noise. And those of you that are in problem stats, does anybody want to chime in and say, what does that mean if I say rand n as opposed to rand? Don't remember, or you don't want to say? It's Gaussian, yeah, it means normal. It means they're normally distributed random numbers, and there's zero mean, and a variance of 1 is the default in rand n. And MATLAB has it by the same name. So now I'm going to pass that white noise through my filter that I designed up above here, and I'm going to do it using second order sections, which is not really something to talk about here. It just so happens John, who's in the comms class here, is also in real-time DSP, and we were just talking about second order sections last night. So I'm using that as a means of filtering it. I could be using L filter, but instead I'm filtering it using this form of the filter. So now that I've got your interest piqued, I probably should just show you what does it look like anyway. What does the SOS look like? It's just a way of organizing the coefficients for the filter into second order sections. So SOS means different things to different people, right? It's a signal, right? SOS, I need help. It means something else that I'm not going to say, only because my father was in the Army and told me what it meant in the Army. But here it means second order sections. So each, this 16th order filter is composed of 8 second order sections, where these are the numerator coefficients of the first section, denominator coefficients of the second one, and then so on down the line. So I filtered that, and so it's now band limited to be noise, a waveform that has a spectral shape that matches that filter. And then I normalize it to try to contain its peak deviation. And I just tried some guesstimations in here, put in a deviation constant of 1,000 hertz, and then modulate it up using the cumulative sum. So run that cell. And just to see that when I add up a bunch of Gaussian random variates, something that everybody that's had prop and stats knows about the central limit theorem. So add up a bunch of any type of random distribution as long as it's finite mean and finite variance, and the central limit theorem says it's going to tend towards Gaussian. But when you add up Gaussian random variates, they are Gaussian already, and this is just the histogram of what's coming, of what's inside this signal MS, and sure enough it is Gaussian. And I'm trying to get the amplitude scaled so that I've got a bounding between plus and minus 1. So that's what the scaling was for in terms of the density height here. The real look at this is in the spectrum coming up. This is just a rough measure of the bandwidth according to Carson's rule, though. If I take Carson's rule and I say W is 1,000, so I'm trying to control this to be a bandwidth of 1,000, and that's what I designed this filter to be, right? Its cutoff is at 1,000 hertz. So plugging into Carson's rule, I plug that in, and I'm trying to make the deviation be about 1 sigma, 1 standard deviation, and that's what I was doing in here, 1 standard deviation, and then this value over here. Plug that in, so df is approximately fd times 1, and then I plug that into here, and I'm expecting that my bandwidth should be the half bandwidth. In other words, not centered on a carrier, but from the center out to the edge should be about 2,000 hertz. So down here I plot it. I use the PSD function, and I am saying this is the spectrum of the noise that's gone through the filter, and then this is the spectrum after it goes through the modulator, and we can see that it's spreading out because it's angle modulation, and this red line is marking the B/2 point, which is at 2,000 hertz. So Carson's rule is approximately verified here. I mean, minus 80 dB down is not where you check out Carson's rule. You want to check it in the neighborhood of around 20 dB down from the input spectrum, 10 to 20 dB down. So this is not too bad. It's just an approximate measure, though. It's just telling you that it is spreading out. And if you were wondering if it really does spread out the more I deviate, all I'd have to do is change one of these values in here, and I could change that to say 2,000. So I'm now, peak deviation is now twice. That density is going to get fatter. According to Carson's rule, this goes up not to double because delta F is what's doubling. So it's W plus delta F, so it's up to 3,000. Then if I plot the spectrum down here, it's noticeably fatter, right? So the harder, the more deviation I put in, the wider the spectrum gets. This was just an attempt on my part to try to understand if Carson's rule is roughly obeyed. This is one of the things that you would have done in lab number 5 and can be done on the computer, just like I'm doing here, but the real fun of it would have been using the spectrum analyzer in the lab. It would have been the best way to do it, although an analog discovery would also work. The field fox is much better, though, and you would have had a chance to kind of validate this with a wideband signal. It's also possible to use this model to just look at the spectrum experimentally from a waveform for a single tone or a double tone. So here I'm setting up a sampling rate of 48 kilohertz. I'm going to generate 100,000 samples. I'm going to set the peak deviation at 1,000 hertz. And I'm going to put in 2 tones, but initially I'm going to put in a tone at 1,000 hertz. And I'm going to add a second tone later, kind of like the example in the notes. And I'm going to put M equal to 2.4048. Now, why did I choose that? Well, if I look at my modulator, I'm going to be using this cumulative sum, and the modulator is going to be set up to have the phase deviation be the integral of the frequency modulation, which is the cumulative sum, 2 pi times fd. So I have to think, what is beta going to be? Well, beta, according to the formula we looked at earlier, is going to be the amplitude of the modulating tone, which in this case is 2.4048 times fd over fm. And here fd is 1,000 and fm is 1,000, so those cancel. So I've got a beta of 2.4048. So I'll generate that signal, and then I'm using my spectral plotting function, my PSD, which just gives me better control over the axes than NumPy's or Matplotlib's PSD. So there's the spectrum. And it's a complex baseband signal at this point. It's not up on a carrier, so it's centered on 0 hertz. This should be down at minus infinity in dB, because we know that the first nulling of the carrier component occurs when beta for singletone FM is at 2.4048. So this is close. It's not quite dead on. It's just a numerical precision issue. If I was to tweak this ever so slightly, it would probably go one way or the other. I'm willing to bet, though, that it's actually going to be worse. Now it stayed about the same. Maybe got a little bit bigger. It just has to do with numerical precision at this point and whether or not I'm making my simulation run proper. I guess that's why I put this other piece of code in here. If I go over to here and just directly modulate the carrier as if it was phase modulation, I could put M in here directly and without doing the cumulative sum. And now it's perfect. See, there's nothing, at least not down to minus 100 dB. This is the exact same as the above equation, except I'm not approximating the integral with cumulative sum. I'm actually just saying the integral of the cosine is a sine, but a sine and a cosine have the same behavior in the modulator, so I'm just avoiding the numerical approximation. But I want to do this, I want to do that, I'm going to take it back to this, and now I'm going to put in the two-tone case. So I'm going to put in, just going to put in 2 for each of these. This will look more like what was in the notes. Beta is going to be 2, and I'm putting in FM1 of 1,000, then 100. So I'd have to blow up sort of zoom in on this, actually I think what I did is I decreased the deviation constant to 100, and then the spectrum is not quite so dense looking. So if I now kind of zoom in on that, we see kind of the clustering like we saw in the notes. I jump back over here for a second. We had these clusters, and that's what we're seeing right here. We're seeing a cluster around the carrier, then around 1 kilohertz with sidebands inside of there that are at 100 hertz, and so on and so forth. I don't know if that's interesting or not. The spectrum of FM, though, is a lot more complex than just linear modulation. Things are sort of convoluted, and I mean that in the sense of convolution. Things are getting smeared out and somewhat confusing looking. But we do know the lines are here at multiples of 100 because that is the fundamental involved with this message, right? If we're putting in 100 and 1000, the fundamental frequency there is going to be 100. And I could mess with this. This is not in the notebook that's up on the website right now. I wrote this out about an hour ago. I was messing around with this. So if you're interested, I can send you the notebook, or you can develop it by watching the video later. If you want me to push it up there, just Slack a message to me, and I will update the notebook later. Now what we're going to do is going to look at some other topics related to angle modulation. The first one is narrowband to wideband conversion. This is kind of a historical aspect of creating angle modulation, where you would generate it more precisely at a lower frequency, say it used to be called an exciter, was the terminology used in transmitters in maybe in World War II, and I don't know, not in today's language, it's not looked at it that way, but you would generate angle modulation by some means that would not necessarily give you wideband modulation. So you would generate it at a particular deviation ratio, D1, and it might be at a carrier frequency, omega C. And then using RF/microwave building blocks, you would go through a frequency multiplier. And those of you that have been in the lab remember that there are multiplier RF blocks on the radio circuits, and they're also on the RF board, right? I'm pretty sure there's a multiplier on that board. There's a doubler on there, as I recall. So doublers, triplers, other types of RF building blocks that can do frequency multiplication. So here we're talking about a times n multiplier, and what does that do for us? Well, when we multiply by n in this RF building block, that n gets applied to the entire argument of the cosine. So the carrier frequency gets multiplied times n, which is what some of you got to see in the earlier lab experiments in the COM lab. But the whole argument gets multiplied. So the phase deviation, phi, also gets multiplied by n, which means that the deviation ratio in terms of angle modulation is now going to be n times d1. And the peak deviation is going to be n times the input peak deviation. So in building a transmitter, like an FM broadcast transmitter, you might have the so-called exciter, or the low-frequency version of your modulator, and then you would go through frequency multiplication to take it up to the exact transmit frequency. And the exciter or narrowband FM modulator would have a very regulated crystal oscillator in it, usually temperature stabilized in some way. Today, people don't do that as much maybe as they did at one time. They might use a rubidium standard or use the GPS clock to get a reference, but the idea of having a temperature stabilized oscillator is still valid. And one of the nice things about this scheme is that you can start with a very precise oscillator, and then you just have to be, you can move it up in frequency, and you can then increase the modulation index effectively by the factor of n. The one downside of this is that if there is a phase noise or noise spectrum associated with the oscillator, that's the narrowband oscillator, its noise is going to increase by a factor of n as well. So phase jitter, as it's called, or phase noise, is going to actually get bigger as you multiply the signal's frequency up. But if you're starting out with a very clean oscillator, that's manageable. Does anybody have any questions on that? It's kind of a interesting topic, and it's just something that should be understood, I think. I think it's one of the fundamental concepts of modulation theory, if you happen to be using a multiplier. And many of you have already experienced that because you use the multipliers in the super heterodyne receivers that I have in the lab to get your LO. Okay, moving along, now we're on the downhill run. We've worked our way up to the end of modulation, and now we're going to talk about demodulation, and that will take us through the end of the chapter when we spend a little bit of time looking at multiplexing, frequency division multiplexing, and phase lock loops get brought in because that's a form of demodulation for angle modulation. So how do we demodulate an angle modulated signal? Well, remember when we were doing amplitude modulation, we had to use a coherent demodulator, or we found out that for AM we could use an envelope detector. And for single sideband modulation, the preferred method was coherent demodulator, which is what you're using in the project. And if you have certain types of message like speech, then you can use carrier reinsertion and envelope detection and so on. So for angle modulation, we are again going to see that an envelope detector plays a role. It's not the only way to go, but for starters, though, it starts off as a black box. So if this is the angle modulation, the wise guy answers to say, what does the demodulator look like? Well, it ends up being this box called the ideal discriminator, and the ideal discriminator is thought of in the context of frequency modulation, but then it can be adapted to angle phase modulation as well. So the ideal discriminator is this equation right here. It just says that give me my signal, and it will go inside and find phi, take the derivative of it, multiply by scale constant, KD, capital KD is the discriminator, gain constant, and divide by 2 pi, and it's going to give us something that's proportional to the instantaneous frequency deviation of the signal. Remember, instantaneous frequency deviation is exactly in hertz is exactly this, d phi dt normalized by 2 pi. So for FM, where the message phase is proportional to the integral of the message, the discriminator is perfect. It's this sort of a transfer function. The input frequency deviates about the carrier, and then the ideal discriminator just puts out a voltage that's in direct proportion to the deviation about the carrier. So, and the slope of that is KD. The thing that should be annoying right now to you is that how do I go in and get my hands on phi? I mean, it's like when you go inside that cosine, you've got omega ct plus phi. So how do you make that work? Well, the phase lock loop will be an amazing way of doing that because it actually is perfect, but it has its own drawbacks. But before we look at the phase lock loop, we're going to consider some alternative methods. Also, before I get into that, for phase modulated signals, you would go through an ideal discriminator and then integrate to get back the phase modulation. So that way you've got a similar type result for phase modulation, where you'd integrate what comes out of the ideal discriminator. So now what we're going to do is look at, in most of the discussion through the next several pages is going to be around frequency modulation. So that's why I'm not really dwelling that much on demodulating phase modulation by integrating the output of the ideal discriminator. But it is the correct approach in theory. It's just getting your hands on that discriminator function is what we have to focus on for a while. So how can we approximate the ideal discriminator? Well, we can use calculus, I guess is what it comes down to. If you want to get your hands on the derivative of phi, so remember the chain rule in calculus, if we differentiate the entire received signal, we'll be differentiating the cosine, and then we go inside that from the chain rule, and we end up differentiating the argument of the cosine, and we get back then, when we differentiate the argument, we're going to get back this. Derivative of omega ct is omega c, and then we'll get the derivative of the phase modulation. And then from the starting point, we're differentiating the cosine to get a sine. That's not really special at this point, the fact that it's sine versus cosine. What is special, though, is that we've got the phase modulate, or we've got the derivative of the phase modulation right in front of us now. The only thing we have to, and we also can think back that what we have here is AM. It looks like an AM signal, right? We have a carrier, and then we have a constant, the carrier omega c, and then we have the message. And if that's all well and fine, then we can use an envelope detector to get back the message. And this is provided that the modulation index is less than 1, or effectively that this condition is met. And this condition, I say down here, is met because it's only reasonable. And what that is referring to, and again, if you would have been doing Lab 5, you would have actually pushed outside this envelope a little bit. But if you think about the spectrum, if FC is up here and the spectrum is sitting up there, the peak deviation about the carrier, which is what d phi dt is when both are divided by 2 pi, that's always going to be much less, but typically at least less than the carrier frequency itself. So that's what I mean by reasonable. So now if we go in and look at plugging in what we have for angle modulation, we have 2 pi AC FM M of t. That's if we're going back up here to look at what is going to come out of an envelope detector when I have the AC out in front and I have the d phi dt. There's also a need for a DC block. When we do the envelope detector, because we have everything on a pedestal when it comes out, and that's due to the carrier frequency. But then a DC block would take care of that. So it looks like that for the ideal, relative to the ideal discriminator, the gain constant, capital KD, is 2 pi times AC. And this is not a really good scenario because AC may vary. If the signal strength goes up and down, then your gain constant goes up and down. So what a receiver design has to also include is a bandpass limiter, something that will limit the input and actually put it into like a clipping action, limit the gain so that it's constant all the time. So you can send it through a clipper and then another bandpass filter to get rid of the harmonics after that. And then you can go ahead and take the derivative of the signal and use an envelope detector. So this is called FM discriminator with bandpass limiter. And I just want to have you think about that a little bit. If you think about an ordinary amplitude modulated signal, the information is in the envelope fluctuations. But in angle modulation, it's working horizontally. So rather than going up and down vertically with the modulation, it's going back and forth in the waveform itself. So clipping the waveform doesn't destroy the message in any way. It actually can be very good, because if there's envelope fluctuations on an angle modulated signal, those will get through this sort of discriminator and they will be audible. In an analog situation or in a digital demodulation, it would be direct interference. So the limiter is a good thing. It's just a high gain amplifier that clips symmetrically, and then to get rid of the harmonics, the bandpass filter removes the higher order harmonics from the nonlinearity or the clipper. All FM radios have limiters. The only time the limiter is not effective is when the signal is kind of weak, which is what happens when you get too far away from the transmitter. And most of us have experienced that, particularly if you're driving from Colorado Springs to Denver or vice versa. Eventually the signals fade out and the signal gets very noisy and choppy sounding because the limiter is no longer able to go into limiting and noise just starts to get through. I was going to try to go through another scenario, but it doesn't apply that much anymore unless you've got an old vehicle parked at an intersection next to your car and you're listening to kind of a weak FM radio station. I'm just curious, has anybody ever heard the ignition points from an old automobile radiating amplitude interference on radio station signals? You'd hear like a pop-pop or a kind of a buzzing sound. Has anybody ever experienced that on a radio before? Okay. Well, the scenario that I'm more familiar with is it can be going under high voltage power lines. When you're listening to AM radio, you might hear that when the signal has become weak, like you're a long ways away from the transmitter. Or it used to occur to me, well, a long time ago, you guys are too young to remember this, we didn't have electronic ignitions. We had ignition points that would open and close as the distributor would turn around as the engine did its revolutions, and the points were actually mechanical contact that would open and close to send voltage to the ignition coil momentarily to make the spark in the spark plug. Well, most of you have probably heard of spark gap transmitters, right? That was the way the first Morse code and things were sent, by just creating a spark gap, and that would generate RF that would radiate. So cars would have noisy ignitions, or a motorcycle in particular might have a noisy ignition, and if it would pull up alongside you at a stoplight or something, you would hear its ignition noise radiating into your receiver. So that's the scenario that I can recall. And why did I know so much about it? It's because my father did amateur radio, so he had to explain all that stuff to all of my siblings when we were growing up and very young. So I had my lessons in that before I even knew I was going to become an electrical engineer, and it hasn't left my brain. It doesn't happen very much anymore, though, because ignitions tend to not radiate like they used to in the olden days. My father trained me on auto mechanics, though, too, so we got to put in points and set the gap on spark plugs and all that stuff. At any rate, moving along, we're interested more these days into digital signal processing based algorithms for FM receivers, and in Lab 6 you will be using the algorithm I'm about to talk about. It's an approximation to a discriminator using a simple approximation to the derivative, and that is simply taking the present value minus a past value. So xr of t minus xr of t minus tau, and that, when normalized by tau, is the approximation to the derivative. If I just leave the tau off in the denominator, then I've got a scale factor tau in the numerator. And if you carry this along even further to the discrete time domain, you can come up with a pure DSP solution based on this idea, where you get at the envelope through a differencing operation. Now, there's also another way of looking at this, which we'll look at a few minutes from now. But now that I'm looking at this, I'm into receivers and discriminators. I should stop before the time ticks down too far and see if anybody's got any questions on the homework problems that are due on Thursday. So I've got my solution sitting here on my other computer, so I can take on any questions. If you're interested, I can also talk about the three problems. It's 8, 13, and 18, with 18 being the most tedious problem. 18 starts out nice and easy in A, B, and C, and D is not too bad. D is pretty much like the example we looked at earlier, where you're finding the total power that passes through a bandpass filter. But then part E asks you to draw the single-sided spectrum and label the amplitude and frequency for each component, which is a bit tedious. I used Python to draw my line spectra plots, and then I had Python in a cell below get me the actual values of the amplitude, and then I annotated my plot by hand with those amplitude values. So you got to figure out how to do that in part E of problem 18. In problem 13, you're given a message signal, and you want to find out what the instantaneous phase, or the phase deviation and the frequency deviation, are of the carrier. So the main challenge there is in doing that sketch. You can do it by hand, of course, but I used Python, so I had to create a piecewise approximation to that waveform using the functions that we have in Scikit DSP-Com SIG-Sys module. So I used, in particular, the step function. Okay, does anybody have a preference? Well, I'll just back up one more. The very first one I want you to turn in, number 8, is very, very basic. It's kind of like the very beginning of the discussion where I was plotting a spectrum. So in that very first problem, what you're doing is pretty much like we did a week ago, where we plotted this spectrum. So you're plotting the magnitude and phase spectrum, and to work that problem, I would go to the Jupyter Notebook and pattern your solution right off of this. That's exactly what I did. I just changed one value in here and maybe changed some of the plot scaling, and I got the answers that they're looking for in problem 4.8. So that one's pretty mundane. The one that's the most tedious to work is 18, but it's not really hard to work in Python. Again, you work the spectrum, you do the bandwidth and power calculation, just like is done here in the notebook. You do this type of stuff. That's pretty straightforward. Part E is just tedious. It's not really hard to plot it. You just have to put the labels on there, the amplitude labels. So my preference, unless somebody wants to direct me otherwise, is to give you an example about how I worked problem 413, which I just did earlier today, as a matter of fact, because I hadn't worked this problem ever before. So it's just some techniques in Python for creating piecewise functions. So what would you like me to do? Go through one in particular, or the one I wanted to go through a little bit of was 13, since both 11 and or 8 and 18 are kind of already hinted at here in the Jupyter Notebook. I was going to add a little discussion right here. But if you don't want any of it, I'll just keep lecturing too. Colton, you said you'd like something, so would you like me to put some comments in for 13? Okay, so here we go. And I will now post this notebook up, so that stuff will get up there. So the first thing, I'm going to take a different sort of a problem, and I'm going to go off to my notes and scribble down what I'm going to be doing. So I'm going to simplify this problem. I'm going to say, if this will stand still, I may want to go to a blank page. I'll go to a blank page. I'm bothered by the fact that I'm having allergy problems right now, which I guess is better than having COVID-19, most certainly, but my nose is starting to itch a lot due to the things starting to grow outside, I guess. Does anybody else have allergy problems starting to get worse right now? No comment. Yes, okay, so you know what I'm talking about. Your eyes get a little bit itchy, and just the way it is. Well, my experience is it gets worse with age. I used to have problems when I was younger, and it seems like it gets worse and worse every year, a little bit worse every year. So I'm going to let this be m of t, and I'm going to do something very simple. I'm just going to let it go up to 2, and then I'm going to let it go up to 3. Then back down again. So this is really just going to be a little exercise in creating a piecewise function, and then I'm going to assume that FD is equal to 5 hertz per volt. And I'm going to assume this is units of volts over here. So you're asked to find the frequency deviation, and the frequency deviation plot is very simple. It's just going to be scaling the m of t plot by FD, which is 5, so that will give you the frequency deviation in hertz. But then in order to get the phase deviation, that you're going to have to get by doing 2 pi FD times the integral from 0 to t of, I'll just say m of lambda d lambda. And I'm going to assume that the constant of integration is 0. So when I start integrating at t is equal to 0, there's nothing that's been sitting inside the integrator to offset it in some way, shape, or form. So what we have to lock our mind on right now is how to describe that. So that's what I'm going to go off and do. Before I do that, though, I have to come up with some expressions. So I need to have, that is going to be a line, 2t, and what is this line going to be here? This is going to be at plus b, right? I'm just saying it's a line, and m is a function of t, so I just have to figure out what that is, and I can just kind of look at this and come up with the answer. The slope is what? It's dropping by 3 in 1 second, so the slope is going to be minus 3, right? Does everybody agree with that? In 1 second it drops by 3. And then what do I need to make the constant there? So when t is equal to 1, I want to be sitting at 3. So I've got to counterbalance the minus 3 I get from the 3t, so this is going to have to be 6 is what I believe, and then I can check that out and see when t is equal to 1 I'm at 3, and when t is equal to 2 I'm at 0. So good. That's just describing the piecewise that we have there. So I'm going to go over to here now, and I'm going to create an axis of time. Let's say A range is going to go from -1 to 4, and I'm going to take steps of 0.01, and then I'm going to create M to be 2 times T times the quantity SS step. So I'm using the step function. This is going to be a step function that's going to turn on at t is equal to 0, and then it's going to go away at t is equal to 1. So that little bit there is going to generate the rising up and then stopping at t is equal to 1. And then I need to generate a second term, which is going to be 6 minus 3t times, and then I'm going to put 2 step functions in here again, one that turns on and one that turns off. So step turning on at t is equal to 1, and then turning off at t is equal to 2. Then I go for it all and just go ahead and try to plot it right away and see if I've got it right. And I didn't do something right. Oops. I typed something wrong in here. What did I do? I'm confused. Not callable. I've got something in parentheses. Oh yeah, I'm missing that. It's thinking that t is a function, right? That's what it's confused by. T is an array, so I'm trying to find the function of an ND array. Yeah, so that's what's wrong with that. Okay, so that looks, does that look right? I didn't draw the picture maybe to look quite like that, but it slopes from 0 to 2 in 1 second, and then it jumps up to 3, and then it comes back down to 0. So that's right. Everybody agree? No comments? So now if I said the deviation constant was 5 volts per hertz, I would just be plotting, I'd have to dress this plot up a little bit, but I would just be plotting to get that in terms of the peak deviation. I just have to multiply by that, and that would be my peak deviation. I have to put all the labels on there. You guys have to put all the labels on, but now the let me get that to move up there. It's not going to do it for me. Move to the wrong spot. Well, let me get rid of that and put it down below. So now what I have to do is plot the integral of that. So, and I have to scale that according to what I said here by 2 pi times FD. So I'll take some help on this if anybody would like to give it to me. We're pretty much out of time though, but I have to go 2 times pi times FD, which was 5. And then I have to get the integral in here. So how am I going to do the integral? Remember what we did earlier today where I was using cumulative sum to make a rectangular approximation to an integral. So does that sound reasonable here too? I'll just accumulate the values that are in M. So I'll do cumulative sum over M. And then to make it be an integral, I have to multiply by delta t. And delta t was 0.01. Put a multiply in there. Why is that so? It's because that's the way I created t. I used a time step of 0.01. So if I go ahead and run this, or plot it, that's my phase deviation then. And it should be believable. It should be two parabolic shapes, right? When you integrate that ramp, it's going to become a parabola, and then you integrate this ramp going down, it's going to become a parabola. It's going to be continuous. Also, we have a jump in the function, but when we integrate a piecewise continuous function, it becomes smoother. So we're seeing that happening right in here. If I put grid on here, that would make it become more believable, I think. So right here at 1 is where one parabola ends, and then we have a slight discontinuity here if we were taking the derivative, where all of a sudden it jumps to a different parabola. So this is the piecewise solution, though. Yep, exactly. For the second part of 13. This is where you have to plot the phase deviation. So I'm just numerically approximating the integral using that right there. That right there, highlighted, is approximating this thing over here. And if you want to sketch it by hand, go ahead, but I kind of like this idea better myself. So I'm really just giving you a numerical tip for how to plot some things. Any other questions that I can go over right now? Any comments? I mean, comments, I guess, about things I talked about early on. I'd like to have you just put in Slack messages to me, but put them on the Com1 channel, because that way everybody else can see what you're each thinking about in terms of how to do things, of how we should run the exam, is what I'm asking about. Because I think it should be a discussion, and this is an ideal opportunity to use the messaging, the open messaging in this whatchamacallit channel, in our Com1 channel. Another thing that I'm thinking about, which may be not acceptable, but it's something I want to offer up at least, is for the final project on Digital Com, I'm willing to keep the same rules for the undergraduates, that you could work in teams of 2 if you felt like that would be good to synergize. And I'm willing to take the 2 graduate students in the class and say, you guys could work together if you wanted to too. We're all on the same footing. Nobody has anything any different. We all have Slack as a means to share and talk about things. So as a matter of fact, if you were to go look at Slack, you're seeing that these 2 guys in my Slack screen here, David and Deshaun, are both our team members in the real-time DSP class, and what they did is they formed this channel. This is a direct messaging channel, so that when they talk to me about things they're working on together in their homework for real-time DSP, it's a threesome, and when we do our video conferences, it's a threesome always. So they bound themselves together, but yet when they did their midterm, David talked to me privately and Deshaun talked to me privately about his midterm, which was under the honor code to only talk to me about it. So you guys that could work together in theory for the last project could do that sort of an arrangement if you want to. And I'm fine with that. This is kind of an exploration, trying to see if this environment gives us an advantage on something, at least. Something different, something that I wouldn't normally be pushing for, because you'd be able to meet each other in a lab or something. Well, that's about all I want to say on that. We will get back over to more on demodulators, and I'm excited about that because we won't go much further, and we'll go through the complex baseband discriminator, which is the next part of the notebook. This is a MATLAB version. We'll kind of work our way through that. We'll talk about some circuit implementations from days gone by, but still are useful and were used in the CommLab experiments that you've been through. This one in particular was in lab number 4. But then we're going to be knocking on the door of phase lock loops, which is a pretty interesting topic, a little bit mind-boggling. This will bring control systems on the scene, a little taste of control systems, bring the use of the Laplace transform into action. And we'll just continue to work our way down. Right now, I don't see anything stopping us from getting everything accomplished that I want to get accomplished, because it winds down fairly quickly. We're actually, in the faster rundown. Phase lock loops will be a little bit confusing, but I've got plenty of tools in the scikit for playing with phase lock loops. So I'm ready to sign off, and I think I'm going to just jump back over to daily, stop sharing. Yeah, hope you guys have a good day too, and I'll be hearing from you, and we'll be catching up with each other on Thursday, and I expect to see a couple of projects come in yet tonight. So bye for now. Where's Lacey? Oh, there she is. It's like as soon as I stand up, she's going to be ready to go. I'm going to start this video processing now.